Hello, in this lecture, we'll define first fundamental form on a regular surface. So first fundamental form on a regular surface, it helps it to determine the length of a differentiable curve on that surface. Okay, so let us begin. Before going to the first fundamental form, let me first define, so what do you mean by inner product on R3? A map defined on R3 cross R3 to R is said to be inner product if this is a positive semi-definite that is this inner product of B with B is always greater than equals to 0 for all vector B in R3, and this is equal to 0 if and only if this B is equal to 0. Second is this map is symmetric that is inner product of UB is equal to BU for all vectors UB in R3. And the third is it is linear in the first coordinate. So that is inner product of lambda 1 U1 plus lambda 2 U2 with B is equal to lambda 1 times inner product of U1 and B plus lambda 2 times inner product of U2 with B, where this lambda 1, lambda 2 are real numbers and this U1, U2, B are vectors in R3. Okay. For example, if I take the inner product of U and B to be the dot product, so then this map, it is indeed an inner product on R3. So in this lecture, so we'll be dealing with this inner product on R3. This dot product I'll deal with. And there are other ways to define inner product on R3, so I'm not going into that thing. Okay. So now I'll be defining this first fundamental form. Let us take a regular surface in R3. Let S be a regular surface in R3, and let us take an arbitrary point P in S. Okay. So now let us take the tangent space of this surface S at the point P. So let TPS denote the tangent space of S at P. On this tangent space, I can define the inner product as follows. So inner product UB, it is nothing but the dot product of U and B, where this U and B, it belongs to the tangent space of S, and this tangent space of S, it is a subspace of R3. Okay, so therefore, so this inner product of this UB, it is nothing but equal to the dot product of U and B. Okay, and now what is the definition of first fundamental form? The map IP from the tangent space of S to R defined by IPW is equal to inner product of W with W is called the first fundamental form on S at the point P. So this W, it belongs to the tangent space. Okay. So note that so IPW is always greater than equals to 0 because the inner product is positive semi-definite, and IPW is equal to 0 if and only if W is equal to 0. So next, let me define norm of this W. So what is the definition of norm? It is the square root of the inner product of W with W. So which is nothing but square root of this IPW. So note that, so this IPW is also called quadratic form. Or this map is called quadratic form on this tangent space of S. Okay. Now let us take a surface patch in S, and with respect to the that surface patch, so we'll find an expression of this first fundamental form. Let U sigma be a surface patch such that this P, it belongs to sigma U. Let me draw a picture. Suppose this is my surface and this is my point P, and I have this surface patch. Okay, so now let us take a tangent vector W at the point P. Suppose this is my tangent vector W. So for this W, I'll get a curve inside the surface patch such that the velocity vector of that curve at the point P is equal to W. Okay. Let W belongs to the tangent space of S at the point P. Let alpha t equal to sigma ut comma bt, where this t, it varies in minus epsilon to epsilon, be the differentiable curve such that alpha 0 is equal to P and alpha prime 0 is equal to W. So I'll get a curve this alpha here such that P is equal to alpha 0 and W is equal to alpha prime 0. Okay. Now let us take this IP of this W, which is equal to IP alpha prime 0. Okay. All right. This alpha t is equal to sigma ut comma bt. Therefore, alpha prime 0, it will be equal to what? So it will be equal to sigma u du dt plus sigma b db dt. So this sigma u, sigma bu, b are evaluated at sigma u0 comma b0, which is nothing but equal to p. And this du dt, dv dt are evaluated at t equals to 0. Okay. Now, from the definition of this phi alpha prime 0, so this is equal to inner product of alpha prime 0 with alpha prime 0. Okay. Therefore, IP of this alpha prime 0, so this is equal to the inner product of sigma u du dt plus sigma p db dt sigma u du dt plus sigma b db dt. And now by the linearity condition of this inner product, what we'll have? Inner product of sigma u with sigma u du dt whole square plus twice sigma u sigma b du dt times db dt plus inner product of sigma b with sigma b db dt whole square. Okay. Let us take u naught v naught is equal to u of 0 v of 0 and let e of u0 v0, so this is equal to the inner product of sigma u with sigma u evaluated at the point P. So all this inner product above, so these all are at the point P. And let f u0 v0, so this is equal to sigma u inner product with sigma p at the point P, and g u0 b0 is equal to inner product of sigma b with sigma b at the point P. This E, F, G are called coefficients of the first fundamental form. In the basis, sigma u sigma b of the tangent space TPS. Okay. Now if I vary the point P, we'll get EUB, FUB, and GUB are differentiable functions on U. Okay. Now let us see why this first fundamental form is important. So let us take a curve in a surface patch of a regular surface. Suppose this is my surface and this is my surface patch, and let us take a curve here. Let us take this curve to be my alpha. Okay. So at each point, I have this tangent vector. Okay. So now let ST is equal to this integration T naught to T norm of alpha prime T dt. So this S is the arc length parameter of the curve alpha AB2 this sigma of U. Or let us take this curve alpha t to be equal to sigma ut comma pt, where this t it is varying in this open interval AB, and this t naught it also belongs to this open interval AB. Okay. Now if I take the differentiation of this S, so ds dt, so this will be equal to norm of alpha prime t and ds dt whole square, this will be equal to square of this norm of alpha prime t, which is equal to inner product of alpha prime t with alpha prime t. Again, alpha prime t, we know that it is equal to sigma u du dt plus sigma b dB dt. So now this sigma u, sigma b, so these are evaluated at alpha t. Now here, I'll just put alpha prime t is equal to sigma u du dt plus sigma b dB dt. Okay. Again, so what we'll have, so this will be equal to E ub du dt whole square plus twice f ub du dt times dB dt plus gub times dB dt whole square. Okay. So this implies that, so if I just write d square, then it is equal to E du square plus twice f du dB plus g dB square. So this formula is another expression of the first fundamental form. So this is is another expression of first fundamental form. Okay. Now let us give some examples. Let us take a plane in R3. So let sigma ub is equal to the vector A plus u times this vector P plus P times the vector Q. So where this A is any vector in R3 and P, Q are orthogonal unit vectors. Okay. Now if I take sigma u, so this will be equal to the vector P here. Sigma b is equal to the vector Q here. And what will be the coefficients of the first fundamental form? E. So this is equal to the inner product of sigma u with sigma u. So this is equal to norm of this vector p square. Norm of p is equal to 1 because p I have taken it to be unit vector. F is equal to inner product of sigma u with sigma b, which is equal to the inner product of this vector p and q, and this is equal to 0 because they are orthogonal to each other. And g, inner product of sigma b with sigma b. So this will be equal to norm of the vector q square, which is equal to 1. So therefore, the first fundamental form dA square, so this is equal to du square plus dv square. Let us take another example. So now let us take a cylinder. So let sigma ub is equal to cos u sin u b. Sigma u is equal to minus sin u cos u comma 0. Sigma b is equal to 0, 0, 1. And E, again it is equal to 1 here. F is equal to 0 because the inner product of sigma u and sigma b is equal to 0. And G is the inner product of sigma b with sigma b, which is again equal to 1. So here also ds squared is equal to du squared plus dv squared. Next, let us take a spherical surface patch. Let sigma ub is equal to cos theta, cos phi, comma, cos theta, sin phi, comma, sin theta. Theta is between 0 to pi and phi is between 0 to 2 pi. So this is a spherical surface patch. Sigma theta, here it will be equal to minus sin theta cos phi minus sin theta sin phi cos theta, and sigma phi, it will be equal to minus cos theta sin phi cos theta cos phi, comma 0. And now if I compute this E, which is the inner product of sigma theta with sigma theta, so this will turn out to be equal to 1. F, it is the inner product of sigma theta with sigma phi. This will turn out to be equal to 0. G, inner product of sigma phi with sigma phi. This is equal to here cos square theta. So the first fundamental form will be equal to d square d theta square plus cos square theta d phi square. This is the first fundamental form on this surface patch which lies on the sphere. Okay, I'll stop here. We'll continue in the next class.